Hello everyone, I am Priya. I'm gonna explain you about light-matter interaction. To understand how light interacts with matter, you must have a general idea about nature of light. Maxwell in around 1850 unified the fields of electricity, magnetism and optics, formulating light as coupled electric and magnetic field oscillations that move with speed 3 into 10 raised to power 8 meter per second. But wave theory alone is not able to explain many phenomena like photoelectric effect, Compton effect, etc. Quantum theory of light came into existence in order to explain these phenomena. According to quantum theory, light consists of very small energy packets. They are small enough to be absorbed even by a single electron and are called photons. Where we see light-matter interaction in a daily life. Interaction of light and matter enables us to see things around us. The images we see are made up of light reflected from the objects we look at. My favorite example to explain light-matter interaction in simple words is the reason that why is the sky blue. Here is how it works. When sunlight enters the atmosphere, a particular frequency of blue light is able to be absorbed by the outer shell electrons of the atoms of nitrogen in our atmosphere. As you know, our atmosphere is composed of 78% nitrogen. When outer shell electrons absorb these photons of blue light, their energy level jump to an excited state. But this is also an unstable arrangement, so the electrons immediately return back to its ground state, re-emitting a blue photon. But these photons are emitted in every direction. In other words, they are scattered, and this is why the sky is blue. But why only blue light is absorbed by the nitrogen and not the other ones? So let's find out. All matter around us is made up of atoms, which in turn consist of charged particles, that is positively charged nucleus surrounded by negatively charged electrons arranged in shells. These shells are called energy levels. Each shell has a specific energy. Electrons require a certain amount of energy to move from lower energy level to higher energy level. Now consider a photon moving towards an object. There are three possible ways of interaction of this photon with object. First, when energy of the photon is equal to the energy gap between the shells, the photon is absorbed by the electron and disappear, causing excitation of the electron from lower energy state to higher energy state. Since electrons do not stay in an excited state very long, the excited electron will soon return to its ground state, emitting a photon with same energy as that was absorbed. Second, if the energy of the photon is higher than the energy gap between the shells, same process will happen as in the first case, but the additional energy of the incident photon is released in another form called thermalization. Third, if the energy of the photon is lower than the energy gap between the shells, photon will pass through the atom without interacting with it, since it does not have enough energy to excite the electrons. This is the case of transparent objects like glass. Forbidden transitions. Interaction between light and matter by the laws of quantum electrodynamics are the basis of a wide range of technologies including lasers, LEDs and optoelectronic devices. But as I have discussed, most light-matter interaction processes are forbidden by electronic selection rules. For example, spectrograms, which are used to analyze the elemental composition of materials, show a few bright lines corresponding to specific allowed transitions in the atoms of that element that can be accompanied by the release of a photon. The dark regions, which make most of the spectrum, emission at those energy levels is not allowed or forbidden. There are new realms of light-matter interaction. With a new study, we demonstrate theoretically that these forbidden transitions can be possible using confined waves within atomically thin 2D materials, for example, atomically thin semiconductors. Some of the transitions which normally take the age of the universe to happen could be made possible to happen within nanoseconds. The atoms itself is much smaller than the wavelength of the light that gets emitted. So the concept used is to shrink the light so that it matches the scale of the atom. A two-dimensional material is used in which light can interact with the matter in the form of plasmons, a type of electromagnetic oscillations in the material. These plasmons are very narrowly confined in the graphene in a way that makes some kind of interaction with that matter. This method can enable the simultaneous emission of two photons that are entangled, meaning they share the same quantum state even when separated. Such generation of entangled photon is an important element in the quantum devices, such as those used for the cryptography. This will serve as a founding piece for the next generation of the studies on light-matter interaction and could lead to further theoretical and experimental advances in the fields of which rely on light-matter interaction, including atomic, molecular, optical physics, photonics, chemistry, optoelectronics, and many others. Thank you.